All right, well, welcome everybody. This is my senior capstone research project, evaluation of Twitter bot detection through semantic representations and deep learning. So a little bit of introduction. As all of you probably know, social media networks have been it's been a grounds for extreme controversy, right? With misinformation, spam, and all kinds of different things. And one thing associated with this is the spread of autonomous programs, bots, right? Now, bots can be defined as an autonomous program, or it could be defined also as a user with bad intentions. So I wanted to take a look at this through the lens of just the language itself. Can we determine if a single tweet was written by a bot or not? So that is the only consideration taken here. This is the only feature that is used through this whole evaluation here. Prior work from Kutagunta and his colleagues, they used a long short-term memory recurrent neural network in 2018, and they used tweet semantics similar to me, but they also used user metadata. One of the difficult parts for this evaluation was that many of the prior work done didn't use just language. They leveraged other features also, such as follower count, the time that the tweet was done, the amount of tweets that the account has made, right? So going forward, I found two different data sets, the Cressy 17 data set, which is widely used for this task of finding bot or not. And down here, we just have the Cressy 17 data set has a large amount of data, right? Just looking, if you look here in the center at the analysis section, the label distribution here, you can see the Cressy data set has a ton of information, a ton of tweets. In specific, almost 6.3 million tweets compared to the Twibot set that has a little under 2 million tweets in the whole data set. So one of the big concerns that I had doing this evaluation was making sure my entire approach was as standardized as possible, right? To get a good tell whether the one-dimensional convolutional neural network is better than the stacked by Lstm, or is better than transformer models in the form of BERT tweet, which is used here. So essentially the workflow, I acquired the data set. The Cressy 17 data set is accessible to everybody online, so you could go and download it right now yourself. But the Twibot 20 data set that was released in June of 2021, you had to contact the authors, and luckily I got in contact and was able to get a hold of them for that. So I got a hold of the data sets. I started my pre-processing, taking a look at the data set, looking at the length of tweets, and other data. And then I went and normalized all these tweets, right? So during the normalization, the normalization for every single model is exactly the same, okay? So I use the tweet tokenizer from the natural language toolkit, and they have an emoji package. So you can take this emoji figure and turn it into a string, right? We can translate the emoticon into a text string, and then any at user at Brian Tuck, or at Luis Martinez, at so and so, those would all be replaced with a singular at user token. The same thing for any kind of URLs; those would all be replaced with HTTP URL. So going forward, the embeddings that I ended up using was they're called GLOVE embeddings, global vectors for word representation. They're very widely used. There are different options, word to vec, fast text, that you could use to embed for the embedding. So going back down through here, the training procedures, use PyTorch. So I was able to leverage my GPU to do the computations on, which sped it up, the computations drastically. And then used Hugging Face. If anybody here has heard of Hugging Face, I used their transformer library to be able to leverage BERT tweet. So I would train the model with the embeddings frozen, right? These are already pre-trained embeddings. So I would train until my validation loss would stop, right? And then I would start fine-tuning those embeddings to stop the catastrophic forgetting problem. You may be thinking, what's the catastrophic forgetting problem, Brian? Well, repeat that sentence a couple more times, and that's exactly what it is. When you're using old information to train on new, all of a sudden your model will completely stop improving for absolutely, there's no interpretable reason why, and this is the catastrophic forgetting problem. So to help alleviate that, that's what I did for that. And then early stopping is used if our validation loss did not stop improving, then we would stop after 5 epochs, 5 iterations through the data set. And then afterwards, we evaluate on the test set, right? So we evaluate on a different, essentially a different distribution of data that our model has never seen before. So coming down here, just looking at the CRESI 17 metrics here, you can see some really interesting things here. I chose only to report the accuracy F measure and Matthews correlation coefficient for this one, but you can see that my best model is the BERT tweet model from my testing down on the Twibot set. So I translated that over to the CRESI set. It's kind of like a sanity check, because when you look down at the Twibot 20 metrics, you're probably like, oh man, this isn't performing so well, right? These people are getting, better results than me, and I'm using, better practices, a better architecture and infrastructure. So this was a little bit of a sanity check that say that yes, my pipeline is working, and it is working very well. So I am competitive with my pipeline using the BERT tweet model on the CRESI 17 data set. Now coming back down to our main focus, the Twibot 20, we see something very, very interesting here. The convolutional neural network and the stacked bidirectional long short-term memory recurrent neural blah, right, are very close. Well, typically LSTMs are typically favored for any kind of sequential processing, right? Which is, it's a perfect fit for our text. So typically LSTM models do a moderate amount better than convolutional neural networks, but you can see we're actually extremely close across our precision recall accuracy F measure and our MCC. But our real rock star here is a BERT tweet model. Really coming in high. It's able to it's the BERT tweet model is able to really balance capturing the bots and humans better, right? Which I'm not really too surprised at, because the transformer architectures are absolutely enormous, right? Compared to, I'm only using a 1-layer CNN here, right? And I'm only using a stacked LSTM here, right? So I wasn't really surprised by that, but I was really surprised that the improvement was not more, is one of the big surprises to me. If you guys have any questions, don't be afraid to interrupt me while I'm blabbering on to you. Is there anything in specific that you guys would like me to zoom in on, or any questions so far? Don't be afraid. Okay, so I'll go ahead and continue then. So going through the network architectures and optimization that I used here, I use a one-dimensional convolutional neural network, right? So essentially, let me see here if I can zoom in here for you guys.
I see PyTorch. So you're using Python?
Yes, yes, I am. All right. So for the convolutional neural network, this is what the setup of. This is an extremely simple view of what's going on. I wouldn't be able to fit everything on here for you guys to see if I were to do the whole layout, right? So we just take a simple input, right? At user, this poster is awesome! Exclamation mark, right? And then we have a dimensionality of 6. So we perform a convolution with a rectified linear unit activation. And then we have different filter sizes, 2, 3, 5, and 7. And you can think of these filter sizes as taking bigrams, trigrams, 5 grams, 7 grams, 8 grams, 10 grams. So we would feed, just one second here, so I can draw. Yeah. Okay, so essentially we would take, for filter size 2, we take these 2 tokens right here, at user this, and this is what is going to populate this block right here. And then we go down through and we'll take at user this poster, and it will populate our filter size of 3. Now the number of filters I used was 100. So each one of these blocks is going to have 100. There's going to be 100 of each of these blocks. So after we do that, we feed it through and we get our feature map. And then we use one max pooling. So we take the max from this feature map, and then we concatenate all the vectors together, and then we perform a sigmoid operation on it, a logistic operation, and we're able to get the singular input. So any questions over that? Anybody? No? Okay, we'll continue. So going to the LSTM here, kind of the same thought process here. We have our tokens that are going to be fed in through each tweet is going to be fed in, each row in our data set, right? So at user, this poster is awesome! Exclamation mark. So we feed that through our embedding, and we propagate through. I know this looks really confusing. So we propagate through all these hidden states right here, right? We propagate through, concatenate, propagate again, concatenate. You can think of this as kind of folding over itself in the simplest way to put it. And then we feed it through a linear layer, or if you've ever used Keras, it would be a dense layer in Keras, same thing in PyTorch, it's linear. And then we would feed it through the same sigmoid function. So with the BERT tweet model, really interesting. It's a transformer architecture, which is really it's really transforming, no pun intended, transforming the world around us currently right now. So I was able to utilize this. So essentially, we have a input embedding, right? One hot encoded embedding that we feed through, and we get the position of each token, and then we feed it through another attention layer. It's called multi-headed attention. We add and normalize, and then a simple multi-layer perceptron. We feed forward, add and normalize again, feed into our linear layer, and then softmax is actually going to be used for this. And then we're going to get bot or human from the softmax, or two labels from the softmax, or sigmoid using the other 2. We're only going to get the 1 value, right? So moving forward, out of all these architectures and all the testing that I ran, the BERT model definitely was the best performing overall, but it was the most computationally expensive model out of everything that I've ran. So the way forward right now is I'm continuing this research at the READAS lab at the University of Houston main campus. Some different approaches that I'm looking at right now are the use of ensembles, meta learning, and positive unlabeled learning. So yeah, I would really love any questions you guys might have, any insights you might have.
I have a quick question. So your research could be used maybe for like fraudulent websites that could determine if, like, you know how some websites are like this fake or scamming people? And if you look at the reviews, they sound like real people, but they're just bots. Could this type of research be used to determine if the comment or the review was by a bot or by a person?
Oh yes, definitely, definitely. That would be like a different use case, but you could take the same approach. One of the things that I did find out very quickly, looking at the Cressy data set here, that was collected from 2009 to 2014, right? It was a really easy data set to work with, right? Minimal effort really had to be put in to get an extremely good score, but the Twibot data set was very difficult. So depending on the application, so an application like that, it'd be really interesting to try this methodology out on it, just looking at the text. But yeah, you could definitely apply the same thing over there. Yeah.
That's very interesting. Thank you very much.
No problem.
What's your future plan for this project? Like create your own, let's say there's a Cressy 17, and there's Twibot 20.
Mm-hmm.
Do you plan on creating your own in the future?
That's a good question. I was thinking about it. I actually have a big problem with the Cressy data set, actually. So this data set is sectioned up into multiple different data sets within itself. So the attributes of this data set, it's a social spammer data set, right? So a lot of the data inside it is duplicated. And even when you split it up directly, like exactly the same way that the author split it up and tested it, you're getting duplicate copies inside the training set, inside the validation set, and inside the testing set, which is inflating the scores. And I actually I took out all the duplicates and reran this and scaled it to the same size as the Twibot set. And it was about 93% accuracy when I did that. But yeah, I was thinking of, maybe taking an angle, more information, right? You're feeding the model more information, so you're gonna get better results because it's able to learn over more information in a much wider distribution. Does that answer your question?
Yes, thank you.
Perfect. Anybody else?
Hi, I have a question.
Yes.
Why didn't you remove the stop words and punctuations?
Oh, yes. The stop words and punctuation, I did try that at first. As soon as I removed any combination, so if I remove just stop words or just punctuation or a combination, all my metrics dropped quite a bit. I think it was about 5 or 6%. So looking at the application inside of social media compared to regular text, like looking through processing like a book or something like that, or a news article, Twitter definitely. It seems that the models, it's really hard to interpret. This is really like a black box. It's really hard to interpret. But all the other studies I looked at, they got the same results also. They as soon as they remove stop words and punctuation, their results essentially drop drastically. Yeah. Does that?
It makes sense.
Yeah.
Yes, it was a great answer. Thank you.
Oh, no problem. Thank you.
Hey Brian.
Hey, how are you?
I'm
Glad
good.
you showed up.
All right. So like actually I have a question about the data sets like so the Twibot like training that one's like I think that's a lot of tweets, right? Like 33 million.
Yes, yes.
So do you think like the score, the accuracy, like the precision are low, right? So do you think it's because of the like the number of the tweets?
Actually, I forgot to mention that the 33 million tweets, that's the total data
Okay.
set. So about it's like 1,900,700 and something of that 33.5 million is actually labeled data. The rest of that is unlabeled data. Yeah, that was a big oversight on my part. But yeah, like I was saying earlier, when I I rescaled the Cressy data set, right, to really fit in the same exact label distribution, right? I scaled it down, same exact label distribution, and the metrics here over here, they were accuracy was like 94 point something. So I lost about 4% when I did that. So yeah, I see where you're going with that, where the more data, better results. But in this case, that doesn't seem to be the answer.
Okay. Thank
Yeah.
you.
Yeah.
This about bird tweet.
Mhm.
It says a pre-trained language model using 12 encoder layers. So what
Yes.
made it become 12?
That's really interesting. That's a really interesting question. I'm not sure why they chose 12, but they have different. So this is considered BERT tweet base. The original BERT model has 12 layers also, but they also have a BERT tweet large that uses, I believe it's 24 layers, but there are also several different variations that use like 12 layers, 4 layers, 6 layers, 8 layers. So the most common theme between all the different transformers, if you look at BERT, you look at Roberta, they all the base model sits at 12 layers.
I see. Thank you.
Yeah.
So I'm thinking maybe the larger the layer, the stringent the model.
Maybe BERT is it's very computationally intensive to train. So when I was running the CNN, I think it was about 32, 33 million parameters, and that'll depend on your vocabulary size also. So for my vocabulary size, this is for the Twibot data set, it was about 32.5, 33 million parameters, and the Lstm was about the same. The BERT tweet model, it was 132 million parameters that we had to propagate.
I see. And the
Yeah.
training time, how long it took to train the data set for Cressy 17 and then the Twibot 20?
On the BERT model?
Yes, I would say I'd like to ask all of them. How long was their training data? Training time.
Oh yes. So all this was done on my local machine. So I was extremely lucky to snag. If you know anything about GPU computing, I was able to snag a NVIDIA 3090 to do the computations on. So using that GPU, each run of the CNN on the Cressy took, oh man, I want to say it took about, oh my gosh, about an hour and
Only
20
an
minutes.
hour.
Yeah.
Only an hour for 6 million.
Yeah.
Oh my.
But that was for the CNN. And with early stopping, I believe I stopped at, all of them stopped around the same time. It was about epoch 26 to 28. So yeah, it took about an hour and 10 for both, for the CNN and the LSTM. Now on the Twibot data set, it took about 25 to 28 minutes to calculate. The BERT tweet model was about an hour and a half each epoch on the Twibot data set, and it was about 4 hours on the Cressy data set. But I only trained that for it. I only trained it for 3 epochs, and the model converges at around the end of the first epoch, and it doesn't improve very much after the second epoch. So I just settled at 3 epochs. But yeah, quite a long time.
I see. Yeah, thank you so much.
No problem, no problem. Right. Any other questions, or do we have some new people in here now, I think?
Yeah, all right, Brian, thank you very much. I like the poster looks really good. It's sketchy.
Thank you, thank you. Yeah, I went through a couple revisions, and Dr. Verma from U of H at the READAS lab, he helped me out too. So definitely hit him up, IPSA. Hit him up if you have a poster you need help with.
Oh, that's good. I will. All right. Thank you very much.
Yeah, no problem. No problem.
Cool.
Hello.
Hi, how are you?
I just had a question about because I'm really new to the deep learning and neural network. So I saw on the picture, on third picture, you see you separate from the original data to multiply data and apply the CNN. Is this just a single neural network, right?
Yes, actually, yes. The CNN right here is just a single, this is a single layer. I know in computer vision, they'll use multiple layers. But yes, for this CNN, you would consider this a single layer. That's it.
So like basically it's just each of the activation function is one single neural network, and like when we apply more activation function is we call like multiply neural network.
Yeah, let me see if I can pull up the drawing thing here again for you. So essentially, I haven't looked too much at doing past one layer. So I believe what you would do for like a multi-layer CNN, you would have the same setup, filter sizes, feature map, max pooling, concatenated, but I believe you would remove your sigmoid activation, and then you would project to another dimension, right? So you would project either up or down. Does that make sense?
Yes.
Yeah, I would double check for sure. Like I said, I haven't dabbled too much in multi-layer CNNs. So yeah, I would definitely take a look to make sure that's right.
Because like in my class, it's like I learned is about like single neural network, and he said about the neural network, but I really confusing about it because every single neural network they have a single filter and multiple filter to apply into one single neural network and one activation function to get the output. So what if I try to put like into two single neural network, it will become like multiple filter applied to multiple neural network to get the same output. But right there after that, it's already get me like four kind of output already. Even though it's I mean four result, exactly 4 result, but actually it's just 2 expect result. It's just like each of the single neural network, it give me 2 result, right? So it's the same with the other one.
So what you're trying to do is, so you have like, what kind of data are you working with? What kind of data
This is a
set?
breast cancer.
Breast cancer. Okay, so
Yes,
that would
the
have,
basic one.
okay, so that would have, if I remember right, like a bunch of different genes, right? I think.
Yes, it's like mean SE, I mean standard error and worse.
Mhm.
So like after apply the PCA to get the filter. So I guess it's the 2 filter, right, or 3 filter. So it's already the multiple filter to apply to the one single neural network. And I try to like, so that is one single neural network, and I apply to another single neural network. So it's already 2 neural network. And I try to like combine them together.
Yes.
I try to combine them together to give the benign or malignant, right? So, and each single neural network will give me the one array is containing benign or malignant. So 2 single neural network give me 2 array, right?
So you're kind of doing, it would be like an ensemble approach, right? So you have multiple networks. So you'd have like your data set X, and then you would have 2, like, I don't know, multi-layer, perceptrons, right? And you would shoot them through both, and then you would want to, you could do like, you could take like the average, you could do average, or you could do voting. You could do voting between the 2. I'm actually working through the same problem on this data set right now. And right now I'm taking the average. So then I would run the data through both, and then I would combine. I found that combining the raw output. So you take off the activation function on these models, right? You take off the activation. So like, let's say each one outputs a vector of, I don't know, 200, right? So you'd have 200 and then 200. So this would be 400. And then you could feed that through another multi-layer perceptron or whatever model of your choice that you want to do the new predictions. So then you'd have your last output activation, signal, whatever, right here. Yeah, but I mean, you could do it this way, or you could keep. On my data set, it was better to do it this way than to keep the outputs. So say you're just using like you're using sigmoid, so you have 1 and 1. So then you feed the 2 outputs into a multi-layer perceptron with an input size of 2 and an output of 1. I didn't see very good results doing that. I found better results taking the raw output and then combining it, feeding it through another an in layer and then an out layer.
Does make sense to me?
Sorry, say that again.
That is make sense to me. I mean, your explanation is perfect.
Okay, sorry, it's a little hard to draw on here. So
I know, because I'm new to the deep learning too. So I have to try to figure it out.
Yeah, it's really interesting, and depending on your application, like everything is so new. Everything is so new. Depending on your application, you might not be able to find very many answers without really diving into it really hard. So
Because
yeah,
the picture of like multiple neural network I see every time, but like when I try to find a work on multiple network, it's like don't have any. It's just a single neural network.
Yep. Yes, you are 100% correct. A lot of my research the last 2-3 weeks has been over that, and I can hardly find anything. I can find a couple things for computer vision tasks, but I can't really using ensembles. But as far as natural language processing with deep learning ensembles, it's really bare right now. The stuff that is out there is from about 2020 to now. So I think people are finally starting to look a little bit further into it.
So like deep learning is like, I mean, computer vision is taking the picture to put to the deep learning to put the output, right?
Yes.
And is it possible if deep learning applied into the like the continuous number of data set? Is it possible?
For image tasks, continuous values.
Yes.
I'm not too sure. That's a good question. Like I said, I've spent so much of my time in natural language processing that I just don't really know about computer vision too much.
I know the computer vision is like I know the basic thing. It's just like taking the picture and searching on the picture on the like if the dog have the ear and I mean they have the more hair than the dog. I mean the cat have more hair than the dog, and so it's the cat. That is I believe that is computer vision and deep learning.
Yeah. So essentially with that, it's actually I do know just a little bit. It's really interesting, but they make the calculations like on the convolutional neural network. The feature map is actually going to be the edges. It's going to be the edges of the picture. Us as humans, when we look at something, we don't look directly at it. We look at kind of the outline of it to be able to tell. Yeah. So that's one really interesting way to think of it. So now that I said that, you're probably going to look at something now in your room or office, and you're like, huh, I am looking at the edges.
Okay, thank you so much for your help. Probably I will learn something from here and apply it to my data. Thank you.
Perfect, no problem. Thank you. Bye.